Hey there everyone, Professor Tomney here, and I just wanted to remind everybody to head over to Chem Complete if you are enjoying these free lecture series. We have available free resources. We also have services for one-on-one tutoring. And right now we're in the midst of doing the Substitution Nucleophilic Reaction course, and we do have a guide available for this. So if you click on Buy Guides on the website, you'll be brought up. We've got a couple of them here. We're working on new ones every month. So the one that you see right here says Nucleophilic Substitution and Elimination Guide. It's available for $5, and you can just add it to the cart. It really helps to support the channel if you have the ability to do this. I'm trying to keep the courses completely free on YouTube so that everybody has a free resource to learn from, because I do believe you should be able to educate yourself for free or virtually free when it comes to this material. But that helps us continue to produce content if you can support the channel. And with the guide, you will get a very detailed set of notes. So it's essentially a small book that I've put together. It's got images that we've used. It also goes into far more detail than the individual lectures do, because I am able to write in great detail here and allow you guys to pick it up. Now, once you get to the end of these guides, and I do have them for others, the most popular one is the unknown structure course, where we use NMR, IR, and whatnot to solve unknown structures. I always have practice problems. So just like in a book, you will get practice problems with very well-crafted questions. Keep in mind that these are the types of questions I would have used on my exams or my homeworks when I was teaching organic chemistry. And then, of course, I include the answer key. So you will get detailed answers and explanations to all of this. So if you're looking for additional practice and you can help support the channel, I greatly appreciate it. And if not, just watching the videos and sharing them with friends that are in class that might be struggling already supports the channel plenty. So thank you very much, and on to today's lecture. Alright everyone, so this is the third lecture in the Substitution, Nucleophilic, and Elimination course that we are going to be going through. And we're ready to start talking about the four major factors that are going to affect substitution and elimination reactions. Now you may hear me as I go through these factors really refer to substitution more than elimination, and that's simply because we're talking about substitution first. But when you hear me talking about the bulk of this, you can also apply it to elimination, because these use the same reagents, they are competing reactions, and then at the very end of the course we'll kind of differentiate when elimination may occur over substitution or vice versa. So the first factor that is going to affect our substitution reactions will be the identity of the leaving group. So we know from our prior lectures that we need two major things for a substitution or elimination reaction to occur, and that is a leaving group and a nucleophile or a base. So we have to have a leaving group and a sufficient leaving group in order to get a substitution reaction to occur. And both SN1 and SN2 have this requirement. So if you keep in mind the general mechanism, when we were talking about SN2, we said that we have some leaving group which we'll call X, and the X needs to leave as the nucleophile is going to be coming in and attacking. It's concerted, it happens at the same time. So because the nucleophile is going to be coming in at the same time the leaving group is leaving, we certainly want a very strong leaving group, a leaving group that has a very good ability to leave without a whole lot of other factors that are going to get in its way. And then the same thing is true, the mechanism is different, but the rate limiting step in an SN1 is going to be that we need the leaving group to leave on its own, and then we will leave behind a carbocation, and that carbocation will be attacked by the nucleophile. So that's the general premise here. And what we're talking about in this lecture for factor 1 is what is X? What is going to be the identity of X when we're looking at this? Well, when we want to take a look at this, we need to understand what makes a good leaving group or an effective leaving group. And this can be summed up in one simple statement: a weak base. A weak base is going to make a good leaving group. Now, if you look at this through observation, you would say, what are some of the leaving groups that you see? So if you're watching this video, you're most likely in the middle of organic chemistry, or you've seen it in your classroom. What are some of the leaving groups that you come across? Well, some of the most popular ones are the halogens. So let's take chlorine, for instance. Right? Cl can be attached to some R group. The chlorine leaves, taking the electrons from the covalent bond with the alkyl group along with it, and then we have a full octet on the chlorine in the valence shell, right? And it's got a negative charge in solution. So, how can we look at this in regards to this being a weak base? Well, go back to general chemistry and consider HCl. So HCl was considered a strong acid. A strong acid has the ability to completely dissociate in solution, right? So it's going to become H plus and Cl minus. Now, what's interesting about strong acids is the complete dissociation means this is not an equilibrium. It's a one-directional, everything goes into the form I've just circled here, right? Alright, so the fact that this is not a reversible reaction means there has to be some level of stability in what lies to the right here on this product side. And in particular, what we're talking about is chlorine and its ability to host this extra set of electrons that it took from the covalent bond. How well can it do that? And if it wasn't able to do it very well, or it was reactive, we would see the ability to go back the other way, and we would reform HCl if Cl minus was not able to sort of coast in solution and offer a stable situation to that extra set of electrons. So, as we learn in general chemistry, if this is going to be a strong acid, we end up with a weak base. And when we have weak bases, they tend not to be reactive. They tend not to interact with much in solution. They're able to just sit and coast in the solvent where they are. And that means that they would make excellent leaving groups. Because what do we want with a leaving group? We want something that is going to depart into solution and then stay in solution in this form. We don't want it interfering with the nucleophile. We don't want it having any type of side reactivity, ideally. And that is exactly what we get when we have a weak base. Now keep in mind that the halides are not the only example. They're an excellent example to start with, and they certainly do make weak bases. However, you could have something else, such as water. Water is considered to be a weak base. It would also be a weak acid, but it is a weak base, and so therefore it also would make a good leaving group. Now keep in mind, we are talking about water in the neutral form. If water is deprotonated, it makes OH minus. And what we just said was that water would make a relatively weak base, but it also makes a weak acid. So if we have a weak acid, the conjugate base is going to be strong. And this is why when you are in class and you have OH groups, your instructor will tell you that alcohols are not going to make good leaving groups. That's because if an alcohol leaves, it becomes a strong base in solution. Strong bases are highly reactive, and that is not a situation that we're looking for. That's not to say that hydroxides can never leave. There are very specific situations where they can, especially depending on the other reagents in solution. However, particularly when you're dealing with nucleophilic reactions, we are not going to consider things like hydroxides or amide ions, which is when we have NH2, okay? Anything of this nature is not going to make a good leaving group, and that is because it is an incredibly strong base when it gets into solution. All right, so the neutral forms, H2O and also NH3, ammonia, if you can find that in the format of R, okay, H2O, like this, and you would have a plus charge on that oxygen at that point, that makes a very good leaving group. Water will happily depart, it will be stable in solution, and it can leave behind the R group. All right, so those would be good leaving groups in a case like that. But you want to keep all this in context relative to Ka and pKa, because that helps you understand what really is going to make a weak base coming from a strong acid. So let's go ahead now and take a look at this table. This comes directly out of the guide, and this is a table of what would make an excellent leaving group down to a very poor leaving group. And these are relative values, right? So we're not actually quantifying this on a scale. If you wanted to do that, you would take an identical reaction and change the leaving group, and then you would monitor how quickly the reaction kinetics proceeded or how quickly the reaction was over in order to test the efficiency of this. Okay, but this is a general scale that we're taking a look at here. All right, so for starters, we have the excellent region, and this includes TSO-, which is a tosylate, NH3, and sulfates. So these, in particular, the NH3 is going to be a very stable neutral leaving group. We get ammonia in solution. You can see water is right next to it in the very good situation. All right, but what is so special about tosylates and sulfates, and what are we even talking about when we say this? Because teachers will usually abbreviate this, and students get confused, and they just kind of identify with the halides, the Br, the Cl, because we all know what those are. So when you get ready to take a look at tosylate, the structure of a tosylate is an aromatic ring. It's a type of sulfate, and it's got the sulfate grouping here, okay? And then it also has a methyl group down here. So this group right here, all right, that I'm about to section off, that right there is the tosylate. And if it were to leave, right, this oxygen would take the negative charge. You get the tosylate anion. Now the reason these are so important is that they are going to be resonance stabilized, all right? So this goes for all of the sulfates. You can put some other group with the, besides the aromatic ring with the toluene methyl there, and you get this type of behavior. You've got a sulfur group with 3 oxygens, and you have the ability to move these electrons back and forth, right, through resonance. And so I'll switch colors here because you also would have another form where you could push those back down, and then you could push these up. So you have really 3 different spots around the sulfur where you could host that lone pair of electrons. And as we know from organic chemistry, delocalization and resonance helps to stabilize charges on structures. So the fact that I have 3 different oxygens that I can spread out that lone pair over is going to be very beneficial in terms of the ability to host it as an anion in solution. And if I can basically weaken this by delocalizing it, I can suppress its energy by delocalizing those electrons, that means that it's going to make a great leaving group because it is very enticed to go out, leave, sit in solution, and it's stable. It can just kind of hang out there as those electrons are delocalized over multiple oxygens. Okay, so that's why the tosylates and the sulfates are fantastic as leaving groups. Now, after that we have iodine. Again, same general premise. Iodine has a very large radius. It's got a large surface area where those electrons are going to be placed. Okay, iodine makes out of the halogens the best leaving group. Water is right along there with it. Then we have bromine, which is good. Chlorine is fair. It still works, but it's not as good as the bromine or the iodine. Fluorine in general, now we're starting to get poor. Fluorine is highly electronegative, and that means it's also going to be usually more reactive. Now, sometimes there are exceptions, and we can talk about them later in the course, where fluorine may potentially become a leaving group. All right. However, by and large, we consider it ranked as a poor leaving group. Now, we have the hydroxide, the amide, hydrides, right, methoxides, all of these types, which would make very strong bases in solution. Those are no-goes. Those are very poor. They're even worse than fluorine would be as far as leaving groups, right? And we already kind of understand why now when we look at it from a pKa side or a dissociation and a strong base. So this is your ranking. Now, what's nice about this, which is not going to hold true for the other 3 factors we discussed, there's a total of 4 of them, is that this setup here is the same for SN1 and SN2. So that is to say that when I look at SN1, this excellent grouping here is excellent for SN1, and it goes all the way down to very poor for SN1, and it's the same for SN2. So they both follow this order. That will not be true for the other three. When we look at the other remaining factors, we're going to find that SN1 prefers one type of format or structure, and SN2 will prefer the opposite. And so you have to keep track of that. But the identity of the leaving group, which is very important, okay, will be the same for SN1 and SN2. So you want to aim for staying on this portion of the table. The better you can get, the quicker the reaction will go, the more probable it is that the reaction will occur. So if I were to take a, let's say an SN2 reaction, and all the conditions are the same, except for the fact that the leaving group is chlorine in one case and tosylate in the other case, the one that has the tosylate should be magnitudes faster. It should be a quicker reaction than that with the chlorine. And that's simply due to the fact that tosylate makes a better leaving group due to the factors we've discussed, resonance, weak base, etc. All right, so that's going to wrap up the first factor. And again, the first factor is the identity of the leaving group. Very important when you are picking out and identifying leaving groups. And it also, just a tip here, many instructors will say, how could you improve the rate of this reaction without changing any of the solvents or reagents involved? And the answer is create a better leaving group. All right. So what you would suggest in one of your answers, if they say that, let's say that they have a bromide there, right, as the leaving group, and they say, how could you improve the rate of this reaction? There's a couple different ways that you could do it, but one of the ways is by getting a better leaving group. Okay, now again, unless you have tosylate or something like that, it may become more difficult at that point, but that's always an option on your table. So that's going to conclude the factor 1, which is identity of the leaving group. Remember to like if the video helped you. I always appreciate the support you guys show us on the channel. If you comment, I'll try to get back to you. Many of you just leave generous comments that it was helpful. We always appreciate that. And if you subscribe and you hit the little bell, you will get up-to-date notifications throughout the semesters. We release these courses for you guys. And one more shout out, head on over to chemcomplete.com, take a look at our free resources, and it is a fantastic way to support the channel. So until next time, we will see you guys then, and good luck with your coursework.